This is part 2 of going through section 1.3. So if we look at, I'm going to go back to the top because a lot of the rest of the section deals with this electricity, this model right here. And so with this simple model, you've got current going this way, and you've got some sort of power source like a battery, resistance, capacitor, and then what they do is the author of this book uses some simple physics laws that you would learn probably in university physics too, although you don't need to have taken that course to understand the math here. So if you have taken university physics 2, hopefully this part makes sense. And if you haven't taken university physics 2, know that those are important things, and you should at some point know a little bit about Ohm's law and Coulomb's law. But eventually, what we get down to is a differential equation describing the energy going across the capacitor. I'm not sure if energy is the right word. I hope I don't mess up my physics terms here. It's been a while. But basically, the current going across E of T is the current from the battery or the power source, and EC is across the capacitor. So that means that you can tell how there's a differential equation tells you how much is going across the capacitor based on what the power source is. And so then we can solve that differential equation. So then it jumps to some other things and it comes back to that. So say you have a system where there is no power source. Then any sort of situation where you were, then this sort of slope field here tells us what would happen. So any starting point, you go to 0 or go to 0. Everything goes to 0 in that sort of circuit when you have no power source. Say you have a constant power source. Everything goes towards that power source. Now that's kind of interesting. You can tell how fast, so the differential equations let us know how fast it goes to the power source by following those arrows. It gets more interesting if you have a power source that's plugged in for a while and then not plugged in, or if you have a power source that's turning on and off and on and off and on and off. And so it's on and off, on and off. So here it starts high, but it goes down to that level, then it's turned off, turned back on. And then say you have a power source that goes up and down a bit, then it would follow that. Now, and then in 1.34, if you're on the HTML version of your textbook, the book gives you this little applet for creating the plot of the slope field and a solution. It keeps the sage all under the hood so that you can just kind of plot different answers there. Now, the last section is about autonomous differential equations. And that's when you have this sort of situation where there's no, if you say you're dealing with x's and t's, then there's no t's over here, only x's. In that case, your slope field is pretty boring, because if you create a slope field, it's all the same horizontally. And so if it's all the same horizontally, then you can describe it one-dimensionally instead of two-dimensionally. And so you can use this sort of idea of phase line. So the last part of this section, I'm going to go through activity 132 with you. So let's do this. So say I have, I'm going to try to make this smaller, and then there we go. Perfect. So there's my activity. Here's my paper. All right. So part A. So 132. So that is y prime equals y times y minus 2 times y plus 3. Okay, so first we're going to graph this, but we don't really care about how high or low the graph goes. We care about the zeros of the graph. So in this case, when I graph it, it's going to have a 0 at 0 and positive 2 and negative 3. And it's a cubic, so it goes like that and that and that. Okay? And I might not have, these probably are much higher or lower, but it doesn't matter. All that matters for making this plot line, this phase line, is to know when the graph is positive or negative. So here, y prime, when it's negative, will go even more negative. When it's positive, it will go positive. And when it's negative, it will go negative. And when it's positive, it will go positive. So then I can turn that on its side, have maybe from, say, -4, -3, -2, -1, 0, 1, 2, 3. So at -3, at 0, at 2, and then that means that you kind of match that to our example here. So it's going down there. It's going up here. It's going down here. It's going up here. So that makes this a source. And that makes this a sink. And that makes this a source. So the reason they call them sources and sinks is because when you're trying to map out a solution to these differential equations, they tend to go towards the sinks or just away. So below this source and above that source, it just goes unbounded. But things are called sources because if you go back in time, if you're going back in time, they go towards the sources. So everything, by back up in time, everything seems to have come from here or from here. That's why we call them sources. So that's part A. Then let's do the other parts. So part B, we have a similar thing, except we've got y prime equals y squared times y minus 2 times y plus 3. Well, now we have a degree 4 polynomial. So then I think I'll graph it over here. We've got 2, 2, 2, 2, 3. And then, so it's going to have a 0 there, a 0 at 2 still, and a 0 at 3 still. And now it's a degree 4, so it does like a U shape. So it goes, from here goes down. And then it's, because it has degree 2, 0 there, it goes like that, just barely touches the line, and then goes there. Okay, so that means here it's positive. So here it's increasing, here it's decreasing, here it's decreasing, and here it's increasing. So now, 3, 2, 1, 0, -1, -2, -3, -4. 0 to -3, it's going up here. It's going down here. Maybe I should be using different colors. I've got all these colored ones. We're gonna have let's do it. This is so boring doing all black. 3, 2, 1, 0, -1, -2, -3, -4. And then let's make our equilibrium points orange. And so we've got 0, 2, and -3. Let's make up red and down blue. So here, up. And then here, it's going down. And here, it's going down. And here, it's going up. So that makes this one is a source because everything runs away from it. But if you go back in time, everything seems to have come from it. This is simply a node now. And then that makes this a sink. Part C, let's get a piece of paper. C is fun because you've got y prime equals cosine of y. So you have, instead of having just a finite number of zeros, you have infinite zeros. Cosine of y starts up high and then so then here it's going positive, here it's going positive, here it's going positive, here it's going positive, here it's going positive. And then here it's going negative, 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 negative. So then if I draw here, so this would be at 0. And then at pi over 2, so it zeroes out, and negative pi over 2, and negative pi, and negative 3 pi over 2, and pi, 3 pi over 2. So I've got zeros at pi over 2, and negative pi over 2, and 3 pi over 2, and negative 3 pi over 2. And so here at 0, it's going up. And then it's going up there and up there. And then it's going down here and down there. So that makes this, this is a sink, and a source, and a sink. Here's a source, and it just goes on forever. Source, sink, source, sink, source, sink, source, sink, forever and ever and ever. All right, now that's part C. And then part D is if we take cosine squared of y, well, that is, instead of every time it still has the same zeros, but then it kind of bounces back again. So it has the same zeros, it just sort of does this. So then it's always positive. Everything's a node. So we have the same sort of thing where you have 0, pi over 2, pi, 3 pi over 2, negative pi over 2, negative pi, negative 3 pi over 2, and it's all red. Wait, but I messed up. Where did I mess up? I messed up because I put in more. There's not that many nodes. There's only nodes. There's not node. I mean, I could have those two there, but so I didn't. Pi over 2, negative pi over 2 are where my nodes are, and 3 pi over 2, and negative 3 pi over 2. Not at like 0 or pi or anything. It's all still positive anyway. So I put in little double arrows there when I didn't need to, but it's fine. All right, so that's activity 132, which we would have done in class if we had in-person class. So I hope that gives you a better idea of autonomous equations and phase lines. All right, that completes section 1.3.